investment idea is about the January effect. This is my table of contents. Okay, have you ever heard about January effect?
Sorry, please press
Oh, I
slide.
forgot.
F5.
Have you ever heard about January effect? Is the phenomenon that monthly average return in January is greater than the average return in the whole year. So if we invest by using this January effect, I believe we can make money by buying stocks at December and sell it after next year, January. And it is also important because it is a good counterexample of market efficiency theory. So it is also academically important. As I said, January effect is a tendency that stocks generate abnormally high returns in the stock market, and it's one of the most well-known market anomalies. The January effect have existed for a long time since its discovery. And this is a very strange phenomenon because theoretically it should be disappear as traders attempt to make money in advance. But, well, it has existed for a long time. And many literature have argued that January effects really exist in U.S. Equity markets, especially in small capital stock return. So my proposition is, if you buy stocks before December and sell it after the next year, January, you will have higher return than annual average return. Let's see the data analysis. The data I use is FN-GAI 3-factor index. Actually, the research about January effect before was basically, most of them was basically based on the simple CAPM model. So I revised it by using French 3-factor model. And the data I used is basically from FN-GAI 3-factor index return. It's a monthly average I calculated. And the index is adjusted model of French model to fit in Korean stock market. And it's from various stocks from Kospi and Kosa. I downloaded it from the website. Data is given in form of starting date stock price as 100 and in form of excessive profit. You can see the equation. Risk-free rate is subtracted in the model. So, and I use 3-factor data from January 2000 through December 2010. I put mu0 is the average of monthly return of the index of every January, and mu1 as the average of monthly return of the index. So I made a hypothesis that my null hypothesis is mu0 minus mu1 equals 0, and alternative hypothesis that mu0 minus mu1 is not equal to 0. So I run no problem. I did the t-test for the mean differences, and I got the p-value of 0.06, and the p-value is lower than significance level, so I thought it would be significant. So I rejected the null hypothesis and adopted the alternative hypothesis. It means the average return is greater than average return of the January is greater than the average annual return, and this is that this can show that my idea is valid. So conclusion is that I found very interesting that this strange phenomenon exists in the Korean market. I found that January effect is basically because of people's behavior. The most persuasive reason of January effect, but not yet fully explaining, is that people tend to sell bearish stock at the year end for tax deduction effects, and then and when it comes to January, then people buy another stocks again with their money. So I found it very interesting, and if we use this January effect, then I think it will generate a higher profit than average. Yeah. And my analysis is further refinement. Like it needs bigger sample size. I used data from 2000 to 2011, but for more accurate analysis, it needs bigger sample size. And I assumed equal variance for two populations, like stock return, average return of annual data, and average return of every January. But I think it's not in reality. And I did not consider any dividend issues like policies.
My research question is, are US stock market momentum, the market strength and cost speed related? If then, how could you use this relationship when you construct your portfolio? So my proposition is, the higher US stock market's monthly return than weekly return, the more profit will be created in Korea's stock market. Of course, sentence is, the higher US stock market's monthly return than weekly return is, it means the stock market has a strength. It means bullish market. So my logical proposition, theory and theoretical backgrounds is like this. Strong stock market momentum creates more chance to get more profit, and Korea's stock market has influenced by US stock market. So I just use these two kind of background, and I just extract this idea from these key literature in three literature, and from this theory and backgrounds to my proposition is like this. Since cost index has influenced by US stock market, investors can make chance to earn the money in market by investing when US market has a strong momentum in its strength. My data is, I just use three data, cost index and S&P index and Korea coal rate, and I just got these informations from these sites, Korea Exchange and Yahoo Finance and Bank of Korea. So I just concept X and Y. X is S&P momentum and Y is cost index. So if S&P momentum is very strong, then cost index will be influenced and it will go up. And my data analysis is like that. This blue line is my performance and C is correct. It means if I just deposit in the bank about 11 years before that, I just use my data from 2001 January 2nd to 2011 May 25th. So if you just put your money in your bank, then you can earn money like this and I just label my data as the start point is 100, and cost P index arose like this, about 350 like this, and my performance is like about 438, about around that. So my conclusion is by using this strategy, by using US index, S&P, and check the power of that, and by using that, you can make the profit in here. So what I have learned in here, actually I just know the relationship between two markets intuitively. However, by researching this, I just found the evidence on it, and so it is very useful for check US stock market to make profit. And these are my limitation of my analysis. My strategy also follows very strong markets. So as you can see, before graph in global finance crisis, I just lose a lot of profits in there. And second one is I just ignore other factors influence on cost B except my data. Last one is it is very hard to get over. It is very hard to get over cost flow. On my graph, my performance almost to follow the cost flows. So if you make more money, then you just need to get over the cost flows. Okay, my presentation is done. Thank you for listening. Any questions?
Okay, thank you, guys.
My research paper question is about Fed model. Fed model is theory of comparing invested rate of long-term treasury notes and expected return from stock market using PAR. The value of Fed model can be the value of Fed model is long-term treasury notes treasury bond rate minus 1 divided PAR. PAR is price per share divided by annual earning per share. Fed model can be used when deciding to enter the stock market. If the value of Fed model is higher than 0, it is better to invest in the treasury notes instead of stock market. On the other hand, if the value of Fed model is lower than 0, it is better to invest in the stock market instead of treasury notes market. So my proposition is that the lower value of Fed model we get, the more returns from stock market we can make. In market equilibrium, expected yield of bond and stock market will go same level. If earning per share divided by price per share is larger than the value of earning per share divided by price per share is higher than bond rate, which means stock market is overpriced. On the other hand, the value of earning per share divided by price per share is lower than bond rate, which means stock market is underpriced. My key literature is here. And the Fed model shows the relationship between interest rate and return on stock market simply, and then we can decide the time when we invest in the stock. We select the stock which has high correlations with the entire stock market, the individual stock will be likely to follow the entire market. My data is daily 5-year Korean Treasury bonds and daily par of Kospi and fluctuation rate of 3 stocks and its effect on Kospi and Kospi index. And I use daily 5-year Korean Treasury news and daily par of Kospi. I get the value of that model. And from fluctuation rate of 3 stocks and Kospi, I get select. I can select stocks which has high correlation with Kospi index. First, I selected the stock which has high correlation with entire market. I choose Samsung Electronics because this stock correlation is 1.77, and I got the value of that model. The top 25 value of that model is minus 4.3209, so I decided to invest on the Samsung Electronics when that model value is lower than minus 4.3209. From this, I choose here from 2001 to 2011. In first period, first period is suppose that I bought one stock at 287,501 and sold 5,545,001. I could gain 98.18%. From this, that model shows relatively high return. The value of that model is low, which means that the stock market is undervalued. We invest at the time when the stock market is undervalued, we can get more return on stocks. However, there was limitations. There were limitations. The lower value of that model didn't always mean high return on stocks. In addition, the stocks which have low correlation with Kospi can be used this model.
Okay, could you please describe series curve?
Explain that model.
Actually, not model.
Yeah, of course.
Stage curve. What is it? How to do it?
Actually, I didn't understand fully that.
Yeah, but you did the homework, right?
Yeah, however, I just used the multiple regression data in there, and I just make that matrix by just using R. So
What?
the matrix is for to make value of that model.
알죠?
So actually, I don't understand the process that I just make.
Okay. Kay, can you describe it? Did you solve it? No, not yet. Although what two stages is clear.
Well, I haven't understand it like fully, but what I've understand is, well, since well, before two stages of the square, we use only like one variable in the equation, but instead of one variable, I guess we use like two variables as the cube, and we find it together.
Okay, so why do we call this two stage? Why is two stage, not one stage?
I guess it's because it is the star is binded in row, so it multiplies twice.
Kind of, yeah. 이현정. Why is two stage? What is one stage, first stage, what is second stage?
I don't know why they call that process two-stage one. I refer some presentation file from the book. They say two-stage model use weighting metrics.
No. So okay, let me briefly go over the stage model. We will possibly on the final exam next week. So in this original model, y equal x beta plus q gamma. So we can write this field as x beta plus epsilon, x beta plus epsilon. Okay. And we have concern that x is possibly endogenous. Okay. X is possibly correlated with epsilon. Okay. So instead of x, we use z. We find z as a instrument. Okay. And we define z star. Okay. G star is where is G star? Okay, so instead of our independent variable xq, right? So instead of xq, we call g. So call z and q as a g star, and we regard that as a instrument variable. So it is two stages because we do the regression two times. In stage one, okay, we regress our endogenous variable x on the instrument. Okay, so in this regression stage one, right? This is projection matrix. We regress x on the space of z, space of z star. So z star is basically this is space composed of q and instrument z. So it's stage one. So once we regress x onto the space of the instrument, then we can, since those z and q are orthogonal to epsilon, basically we can make this x hat, which is also orthogonal to epsilon, right? So anyway, what we do is basically we regress endogenous variable on the instrument, and then instead of that original text, we use x hat, which is projection on z as a new independent variable, and we do the regression again. Okay, so it's stage one, and then stage one and stage two is this. Okay, stage one regress x on z instrument because x is orthogonal. So X is endogenous, so we regress endogenous variable to the space orthogonal to epsilon, and we collect this new projection image of the X, and use that projection image as a new independent variable and use it as a instrument into the regression again. Okay, in a two-stage regression, instead of X star, we can also put X head over here as well. Okay, so in a sense, instead of X, we simply plug X star. Okay, then we can do it to the OLS. Okay, so it's stage 1. So stage 1 OLS, stage 2 OLS. So the same to. It's the same to. Very long, but actually not complicated. Okay. Anyway, yeah. Yes. Thanks. So it doesn't matter whether we have head over for this or one. So the two-stage curve is kind of instrument variable. So to compare this one instrument variable regression, we use X head instead of Z with the instrument. And we use two-stage risk square method when we have instrument more than the number of intelligence variables. So we wanna use all the information in instrument. So to do that, actually we have to do two-stage. So it is two-stage RS, two-stage risk square. And actually there's a three-stage risk square method. And not many people use that. So three-stage risk square method is straightforward extension of two-stage risk square method. So the relationship between three-stage risk square is to two-stage risk square is basically similar to the relationship between GLS and OLS. So this is three-stage. So in three-stage model, other thing is all same, but we actually use this one. We basically estimate through two-stage model. Basically, we basically estimate variance covariance matrix and use that variance covariance matrix to construct kind of GLS estimate. And three-stage. It's conceptually very similar to the GLS. Any question? No. It's simple, right? And the full information maximum likelihood estimation. Okay. Again, this is also seemingly very powerful method, but actually not many people use it. Okay. So again, our equation looks like this. That By equals Cx plus B. Then we can assume that alpha is IID across time and 0 omega. Given this error structure, full information maximum likelihood estimate is simply like this. So what people does is they simply maximize this over some structural parameters. An advantage of each method, full information maximum likelihood include cross-equation restrict that 2 SLS, 3 SLS, or IV do not. Okay, so FIML allows for non-linear eventually. Okay. So any restriction, so basically we maximize this over all the parameters and B, C, or actually you can impose very flexibly any restriction you want. So it is very flexible. But problem is that this full information maximum likelihood estimate is very sensitive to the misclassification error. So we have a wrong model, we can get very wrong answer. There is a small sample bias, and two-stage it has small sample bias. That's why people use two-stage LS over three-stage LS or full information maximum because two-stage LS is basically easier and because it is robust. And all simultaneous execution method track the efficiency in LSE for consistency. So in some sense, they are full information maximum likelihood estimation for three-stage least square method are more efficient than two-stage least square method. The problem is that they are more sensitive and in the small sample, they are subject to more errors and more difficult. Next, qualitative choice model. This is very important. Okay. Now, in the qualitative choice model, from now on, in our data set, there is some limit. Okay, there is some restriction on the dependent variable. Okay. So consider the problem of whether to enter a labor force or not, whether to get a job or previous, right? Okay, or whether to marry or not, whether to live a married life or single life, or whether to commit a crime or not. Okay, so it is like a binary choice model, do something or not. Okay, then our model basically we are estimate when people are more likely to do something over the other. This is qualitative choice. So it is, this kind of model is to make a public market to buy some goods or not. Because it is discrete, now we need alternative method estimation because linear model doesn't work anymore, right? So suppose it is a marketing model. So suppose this is X. Suppose this is X. So X is like quality of some quality, and Y is basically buy a good or not, something like that. So suppose we could buying decision as 1, and suppose we call not buying, okay, not buying decision as 0, okay. And as the quality increases, more and more people buy, right? So basically data will look like either 0, okay, or sometimes 1, okay. As the quality increases, we have more 1 over 0, something like this. So data will look like this, right? So if we use linear model, then I think it wouldn't work, right? So dependent variable should be either 0 or 1, okay? And it cannot be negative number or cannot be positive number, right? So if we use a linear model, there is some problem, okay? So basically we want to fit the data in something like this. Let's define there is some underlying model such that yi star equals xi beta plus epsilon. And yi star is the kind of a relative value of doing something. Okay, if it is married or not, this is value of marriage over single life, value of committing crime over not committing crime. Okay, so it is underlying value, and people will do something if this underlying value is great enough, right? So I mean, in reality, we can observe only the data whether people marry or not, right? And we can maybe think some underlying models such that people will marry only when the value of marriage is greater than threshold value. And where yi star is a way to doing it, and let's say alpha so and this epsilon, suppose epsilon is distributed with some given function f, and define the set of parameter with theta is beta and alpha. So basically we want to estimate this beta and alpha. And in data, okay, the problem is that if we can observe this value directly, value of marriage, okay, suppose it is model about marriage. If we can observe value of marriage directly, we can simply run the regression and we can estimate the beta and alpha, right? But problem is in reality we cannot observe the value of marriage. instead what we can observe is whether people marry or not. Okay, so we can in data. Okay, so it is called indicator function such that if value of marriage is greater than 0, people will marry. Okay, so yi becomes 1. If value of marriage is negative, people will not marry. So it is 0. So it is indicator function such that if the argument in the first hold, it has value 1. If the argument here doesn't hold, the value will be 0. Any question until now? This is the most important part to understand. Yeah, so there is a distinction. There is a true underlying hidden model and the data that we can observe. So data is binary choice, right? Marriage or not. Okay, get a job market, get a job, or go to religion. Commit a crime or not. Right? Become a criminal or not. Study or not, something like that. But yeah.
If people think that value of marriage is they should not marry, then the yi star becomes minus, or
I mean, so it is setting. So maybe in reality there should be some threshold value. Like if value of marriage is greater than some value, people will marry. Okay. But the thing is that if there is a constant, we can simply move constant to the right hand side. So we can always normalize this thing as zero. Okay. So maybe we can think the value of net value of marriage. Okay. So net value of marriage is positively different marriage. Right? If net value of marriage is zero, to make people will not marry. Here the I means people, right? So there are data for like the number of 10 people, for example. So it is I become from 1 to 10. So out of 10 people, some people married, some people didn't marry. Any question? Yeah.
Where's the F and that?
It's the cumulative distribution function of S1. Okay, now let's think about the probability of marriage in this case. Okay, in this case, suppose we have data about X. So in this case, now we can observe this X, right? We can observe this Y. We cannot observe yi star. We cannot, and we have to estimate beta and alpha. Sorry, I have to estimate beta and alpha. So now let's think about the probability of marriage. Okay, for some people I. Okay, so some people this person has a characteristic about xi, like how pretty she is, or how handsome he is, or how rich, whether he has a good car or not, good house or not, or something like that. So x is like a characteristic of a person. Okay, so given a characteristic of the person, we can think about the probability of marriage for that particular person. So yi becomes 1. So marriage means these people marry. Okay, marriage means which means people are married. So for these people, value of marriage is positive, right? So this should be greater than 0, not 1. That's error, right? So right, yi1, which means that yi star should be positive, right? So this should be positive, right? If yi star is positive, this whole thing is positive, which means that xi beta plus epsilon I is positive as well, right? This means, okay, this epsilon I is greater than minus xi beta. Which means that, okay, which means epsilon, the cumulative distribution function of epsilon is f. So it is a probability that epsilon is greater than minus xi beta. Therefore, this probability you can specify with 1 minus x minus xi beta, right? So this is probability. This is the probability density function of the epsilon. So suppose this is xi beta. So this means this is the probability of minus xi beta. So this is the probability of this area. Right? Probability of this area is 1 minus probability of this area. Right? Probability of this area is 1 minus xi. So probability of marriage given characteristic F is this. Therefore, probability of single life will become like this. Right? They should be n to 1. Okay. Now, suppose we have a sample of yi, whether suppose I is value or not, and we give data of the xi. Then basically log likelihood function would be like this. Okay. So for given data I, okay. Given data for person I, okay. So we have data I from 1 to n. So for particular I, the probability that we observe this data should be 1 minus. So it is probability marriage. If probability if a person married, we code that as 1, right? So this, and then okay. Therefore, if f is a cumulative probability density function, given the characteristic of x, the probability that we will observe this particular data is specified this way, right? If this person I is married, then yi1, right? So only this term survives, right? And this one is 1 minus 1, so it is 0. So this whole thing is 0, right? If a particular person does not marry, yi equals 0. So this is 0, this whole term is 1. So this is 0, 1. So only this term survives. So this is the probability of not married, right? Therefore, this is the kind of way. So this whole term is probability of observing this particular data, right? Now we have this data from I to n, right? So this is probability for person I, and we have n number of data. So we have to basically observing this whole data to be okay. Multiplication of this thing from 1 to n, right? So this is probability of observing this entire data set, right? So if we multiply, if this data are independent of each other, right? If we had multiply probability of observing each other, and if we multiply this probability all together, then it is probability of observing all things together, right? Okay. And then this looks too complicated, so one simple one way. So basically, so it is a probability of observing this whole data, right? So basically, in order to, our final goal is to estimate this beta, right? And since this is the probability of observing data, the correct beta would maximize this whole probability, right? Because you already observed this data, right? So basically, in order to estimate beta, basically we wanna maximize this over beta, and actually f is also function of alpha, so alpha. Right? Again, this particular thing is probability of observing this yi, xi. This whole thing is probability of observing this entire data set. And we wanna choose a parameter such that parameters that maximize the probability of observing this data actually, because we already observed this data, right? So this is our goal. But maximizing this function is too kind of complicated. So the identical one is actually maximize beta and alpha over log value of this whole thing. Okay. And it's multiplication, so we take log in everything because summation, right? And this one becomes summation, so we have this one. Therefore, basically we wanna find beta and alpha, then maximize this whole thing. Any question? So this kind of method is called maximum likelihood estimate. Okay. This part is likelihood. actually probability same, likelihood of observing together. And when you want to choose a parameter, then maximize likelihood or probability of actually observing this data. And the maximum likelihood estimator is very intuitive, it's very good, and it is very desirable. It has many desirable properties. They are consistent, efficient, and asymptotically removal. Okay, so this is our basic approach. Now, next step is another technical. We want to choose appropriate app, right? What kind of app we want to choose, and if we, depending on what kind of functional form we choose for app, we can basically simplify another model. So suppose f looks like this. Okay, suppose f looks like this, and this kind of function is called logic distribution. This one really looks CDF because if Z is very large, this is very large, this one will convert to 1. Right? If Z is very small, very negative, then this one will convert to 0. So it is always between 0 and 1, and it is monotonically increasing function. So it looks like two probability density function. Okay. So suppose f looks like this, then simply in the log likeliness method, okay, simply we plug this logic function into this, okay, into this, and see what's going to happen. Then we have looks like this, okay, and this term can be simplified into this one, okay, and this term is same to this one, and then we have this, okay, we have this, so so we have this one, and one is this part. And this part can be simplified into this one. And for this one, we multiply exponential of xi beta to the denominator and numerator, and this one becomes this. And if we again multiply xi beta, denominator and numerator, this one becomes this. So once we have this one will become to this one, right? Yeah, so basically we can simplify the equation looks like this, and all we have to do is take get the maximum value of this one, get the value of beta 10, maximize this whole thing. Okay. Any question?
So the exponential of minus xi multiplied by beta is same as exponential of x, plus xi multiplied.
No. It shouldn't be same. So again, let's go to simplification of x line by line. So first line is simply put that equation into original equation. And second line is instead of 1, we use this one. This is 1. And line 3, okay, we consider this one, so this and this cancels out. So we have this one. And this one is the same to this one. Okay, once we have this line, now to the numerator denominator we multiply exponential xi beta. Okay, then this becomes this, so they are same, and this one becomes this one. Okay, and after this line, so basically we decompose this division into the minors, right? So log exponential, so cancels out with the xi beta. So this term will be combined into this one, and it becomes this one. Okay, so we want to maximize this one over L. Oh, okay, we want to maximize this L function with respect to beta. And we know how to maximize this, right? In order to maximize this, we take derivative, we do the calculus. So first order condition is, okay, we take derivative, so take differentiation of L over beta. We have, for this part, it is easy, so we have only y, ix. And division of this one is a log function, or calculus of the log function becomes fraction. So this part becomes this. Okay. So we put as there is x, so we put this y, I, and this one together, and this one is actually probability. Right? Okay. This is the probability of xi. Okay. You remember logic function. This logic function looks like this. Okay. So we denote this one as a pi, and actually pi is a probability of yi equals 1. Right? yi equals 1. So basically, we have therefore very intuitive relationship. So yi is either has 1 or 0. Pi is probability, kind of probability that yi becomes 1. Okay, so we want to minimize distance between the data, 1 or 0, and probability becoming 1 with weighted algorithm x. Thus, we can think of this first order condition as the orthogonality condition. Residual should be orthogonal to xi. So this is kind of residual error term. So basically, we want to fit. I deleted it. So it is the basically error term. Residual error is 0 and 1 and the probability. So this is error term, and the error term multiplied by this xi should be and increase summation which we kind of orthogonal error condition. So we can regard xi kind of instrument. It orthogonal to the error term. Any question? If I give it to you, can you do this one as a homework? To do this one as a homework, basically, you should be able to solve this problem, or you should be able to do some maximization with R. In R, and by the way, in R, I think there is a logic. It's also possible in R. Actually, I usually write a code that directly maximizes this thing, but I think in R there is maybe pack for this binary choice model. Okay? Private binary choice. Okay, we didn't know private on that. So logic regression. Okay. My data, GR initial. Okay, so GL, not GLM. Okay, so there is a very convenient function called GLM to do this integration. Okay, logistic regression with R. Which means that you can do homework.
And how do you get the data?
Yeah, that's the problem. I am thinking about the binary choice data. In stock market data is all continuous, right? It is not 0 or 1. Is there any binary data? Is a baseball data. So it is baseball data, and I think there is the baseball data is enormously rich. In United States, for major league baseball team, there is actually several consulting companies or quantitative consulting firms that provide consulting service to major league teams about daily data analysis. So when the feature is like Randy Jordan or Pedro Martinez, then what should be their lineup for the hitter? If they play against Yankees, then what kind of player they put on the lineup, something like that. So there is since baseball data is very rich, there is a very good market about quantitative consulting for major league baseball. In Korean market, we have only 8 baseball teams. the market is too small. And then this market is too small, so they don't have much incentive to collect a lot of data. But still, even in the case, the baseball still has the most, I think they have the richest data than the world sports. Let me find whether there is interesting data. I don't know how to get it. There should be some Excel data. Okay, anyway, I think there is data, so please find it yourself. So let's make a loading model like this. Yeah, but really, you mean the distress data? Yes. But let's use more interesting one. Okay, instead of finance data, let's use baseball data. So okay, go to koreabaseball.com and select your favorite baseball. Select baseball team and construct very simple one. Okay, so ignore draw. Okay, there's win or lose or draw. Okay, so get rid of draw. Okay, then find the probability of winning for your particular team. Okay, logic model. So next week is our final, okay? So next week we have exam and homework. Oh, it's open book exam. Okay. Yeah, no problem. So please remember, it is open book exam. You are not supposed to go on the web. So the thing is that you have to print out all the class note. Class note, and you can actually see it. And you can also bring statistical econometrics, and you can use it. But you can refer to web resources. You cannot use Google search, or you cannot access your previous code. Does it sound fair? Actually, you can refer to your previous code, but you have to also print out. Okay, so print out everything, and you can refer to only print out materials. Okay. Not digital materials. Okay. Estimate logic model we go ahead and use So this logic model is very simple. So I'm a fan of Kia Tiger. Okay. So there is 8 baseball teams, so which means that there are 7 competing teams. So sometimes Kia Tigers plays against SK, and then LG and Busan, and Nexen. So when Kia wins a game, it is 1. When it loses, it is 0. Okay? And the dependent independent variable is like this. So we have 7 dependent variables. So when Kia plays so with Kia is alpha 1 plus delta 1 SK plus delta 2 LG plus something like this. So in some particular game, yi, xi look like if Kia wins against SK, then it's 0 and x is like SK1 and LG 0 to Sun 0, Nexen 0, and something like that. If a Kia plays a game against Hanwha Eagles, and if it loses, then yi becomes 0 and this one is 0, 0, 0, 0, and 1, something like that. So I don't force you to select the Kia Tigers, okay? You have to choose your own favorite team and to go model. Okay? Any question? No. Pretty straightforward. And then note that for the linear model, we could interpret the beta as the sensitivity of the y over x. Right? It is slope of the y over x. So in case of linear model, we have this. But in case of logic model, we have now expected value of y I given s is actually probability, right? Probability of y I equals 1 given s, and this probability is this logic function. Okay, this logic function. Therefore, if we take derivative of this one with respect to xi, then we have this whole thing. So basically, it's pi probability of 1 plus 1 minus pi and beta, which is different from beta. Right? So when we interpret the coefficient in the logic model, we should be very careful. It is not simply the slope. It is p1 minus p beta. Also note that when we consider ratio of probability of 1 and 0, then actually we usually call this, sometimes we call this probability as the odds ratio. Then log of odds ratio is actually linear function. Now next, the probing model. Okay, in the logic model, the epsilon is distributed with cumulative distribution function of epsilon is logic function. Okay, in the probing model, we have more familiar cumulative distribution function, which is normal distribution. Okay. So now the error term is now cumulative normal distribution, and this epsilon, sigma epsilon is standard deviation to the normal distribution. So instead we can use this one. So again we plug this one into this previous equation, then we have this thing. yi log 1 minus big pi minus xi beta over sigma epsilon plus 1 minus pi log pi minus xi beta over sigma, right? But actually we can rewrite this one as this one. Again, we can rewrite this one as this one. Okay? By getting rid of minus sign. Now we have a similar dilemma. Okay, we can always estimate only the ratio between xi and sigma, right? So they always go together. Therefore, for convenience, okay, we usually set sigma as 1. Right? Then the L function simply becomes like this. L function simply like this. And then given this L function, okay, if we take derivative, then we have this one. Okay, so this is the cumulative distribution function, and it is just probability density function. Probability density function is differentiated to cumulative function. So this one, and we have this one. Now we can collect xi together. Okay, then we have equation something like this. And basically we can regard this one big pi as a probability of observing at 1. Okay? Thus again we can think of this first order condition as an orthogonality condition. Okay? So this is, since this is probability of observing 1 and this is y is actually 1. So it is error term. And so you can regard xi multiply this one as the some sort of integral. So it means these error terms are orthogonal to this whole thing. And note that again, for this model, if we take derivative of yi over xi, then it's a new probability, and we have this thing, and differentiation of big pi cumulative distribution function is probability density function, so we have p xi beta and beta switching different function. Again, the coefficient when we investigate, when we use binomial choice model, we should be careful. What we do. 토빅 모델은 이제 비슷한데 consider a model for a number of hours worked in a particular week. Okay? Let yi be the observed number of hours worked by person I. So yi star equal xi beta plus ui, and yi is max 0 yi star. Okay? So it is natural because you cannot work negative hours. Right? Working hours should be always positive, so it cannot be negative. But of course, it is your maybe desired working hour, so you can have a negative value in some case. But in data, actually, we never observe negative working hour. Right? So in the real data, we can observe only truncated data. So in this situation, suppose you are distributed with normal distribution like this, and the log likelihood contribution for the observation I is first when I equals 0. When I is equal to 0 means we observe 0 working hour, right? And person will not work. Okay? Person will work 0 working hour only when the value of working is negative, right? Value of working is negative. So people will not work when this is negative. So when this is negative, it means UI is less than minus xi beta. And the distribution of that looks like this. Right? This part is exactly the same to probit model. Okay. Now this part is slightly more complicated. So in this case, when yi is positive, okay, then we actually observe true value of working hour. And this is the probability value of probability density function. Now it is not cumulative density function. So it is probability density function itself of observing a particular data yi and xi. So this is log likelihood function. So all we have to do is again we add this one over all I and maximize this whole thing over beta and sigma u. Then we can get a maximum likelihood estimate. So again, to summarize it again, so we can observe only data when it is positive. So when it is 0, we have like a negative working hour. So value of working is negative. So in this case, it indicate the function of y equals 0, and it is probability that yi is 0, okay? Or yi star is negative value. And it is a probability, kind of probability of observing a particular point yi. Now, Pauly-Quantum's discrete choice model. Now, in the binary discrete choice model, now the dependent variable has only two possible values, 0 or 1. Right? Now, we consider a set of problems where the dependent variable can take on more than two possible values. And we consider three types of models: multinomial model, ordered model, and count model. So, multinomial model is like give example like occupational choice, car brand choice, transportation to work, and choice of car anywhere to live. So in our previous binary choice model, it is like working or not. It is you on this, working or not, buy something or not. Right? Now it is multiple choice model. So in the previous case, it is OX problem. So it is multiple choice problem. So suppose we have like four brands, from Hyundai or BMW, and then Ford and Toyota, and suppose we have a four choice model, and maybe in the data we can observe a choice of a particular brand. Right? In this case, it is not simple OX problem, but it is multiple choice problem. So in case we have data something like this, now the question is how to estimate it. So approach is similar to previous binary choice model basically. So suppose Yij is kind of a value. Suppose it's kind of value of consuming a particular brand. So Si beta, Ij. So Sij is kind of Sij is brand characteristic. If it is marketing problem, it is like brand characteristic of a particular choice for particular data for Yij. And this Zi is particular variable at the for I, and J is particular coefficient for brand J. Okay, so I is, you can regard I as a people and J is brand. Okay, so it is a observation specific, so it is brand specific parameter. So suppose Xij include like brand characteristic or brand characteristic, and Zi is kind of consumer characteristic, whether a consumer is male or female, age of consumers or male. And our goal is of course to estimate this beta and gamma. And then of course in real data we cannot directly observe a particular value. We cannot observe value of the brand itself. Then we will observe what people actually buy a particular brand J. And for others we will they are zero. And then again, epsilon I is suppose it is distributed independently, identically, and let's say its cumulative distributed function is f. So given this setting, then I'll probably how to estimate it. And yeah, given this example, and we observe yi, xi, and zi, and we want to estimate parameters which is beta, gamma, and parameters in f. Okay, first, we can note that we can not identify all the elements of gamma because we get to only see a measure of the value relative to each other. So basically, we cannot observe we cannot identify all the parameters here. Therefore, we set at least one of the elements in gamma as 0. Okay. So basically, it is choice model. So in such a we can observe choice of the people over the brand. So the choice implicitly means that the choice model itself implies that what matters all is the relative value of each other, not absolute value. And this Zi, gamma I is kind of brand specific parameter. The brand specific parameter. So since relative value matters, what we can observe is only the gamma I minus its company brand. Parameters for company brand. Okay. So So usually we set at least one of the element of gamma Q, and that becomes the benchmark problem. So any probability that Yij equals to 1, which means that person I choose probability that person I choose brand J, okay, given brand characteristic and other, which means that Yij star is greater than Yik for all competing brand, right? Ij, which means that Xij beta Vi gamma J plus epsilon Ij is greater than all K. And we rewrite this, then you can say probability of Bijk should be less than epsilon Ij minus epsilon Ik for all K. And here, Vjik means Vik minus Vij. Okay. So it is relative value of K over J for person I. And then Vij here is simply Xij beta plus Vi gamma J, and given this setting, we can write relative value of J, relative value of brand K over J, and we can simply write that as this. Okay. And as this example clearly shows, only the relative value of the gamma man. Now, this is probability, so we can write this as probability that this is less than this. So for given parameter for epsilon Ik, in order to estimate this probability, we can only simply integrate away this part, okay, and we can candidate it. So we can use this probability. So in some sense, it is conceptually not so difficult. I think even R, I think there is a multinomial logic model available. R. So M logic, you know. Yes, M logic, brand female alienation theorem. So actually in R, you can do multinomial very easily. So to explain multinomial logic model, multinomial model logic model assumes that this error term in the model is extreme value distribution, which means that cumulative distribution function for this epsilon looks like exponential of exponent minus exponential of this error. Okay, which means that probability density continuity is simply derivative of this with respect to epsilon looks like. So if the error term is distributed with this extreme value distribution, then this equation simplifies to probability of choosing probability that person I choose brand J given Xi, Z, E. We can simply specify the probability like this one. Okay. In this case, this Vij part, we can regard this Vij, actually exponential of this Vij part as value of something, value of brand. So this is very intuitive. So probability choosing of brand J is brand J's value over all of its competitor values. So it can regard it as kind of brand share of the brand relative market share. In a person's mind, market share in a person's mind or some kind of brand. So it is easy to evaluate, and this model is called multinomial logic model. So this basically, since this is the probability of choosing a particular brand J for person I, therefore log likelihood function is we can simply sum this up across all the data. Okay. So first, the log likelihood continuity for brand for person I is basically this is Yij, we can either 0 or 1, whether a person choose J or not, and this probability, this one is probability. So basically as them all across all brand, this part then we will have log likelihood contribution for person I. Okay. So for person I is log likelihood function, and we can simplify this on this. Okay. So Yij log exponential Vij over them is Yij, and this is fraction, so we can decompose it minus or log exponential, so they cancel out. So we have Vij, and this is minus log or summation of its two values, exponential of these values, and then we decompose this. We separate out over minus sign, then we have this, and again we can correct this one, and we separate it out this yi here, and then you can keep simplifying. We have this one, okay. And then since this is log-like contribution of I, then we have data for all the people. Then next, once we simplify this, and we can add this data or this likely contribution for all people. And if we can derivative of log-like contribution of person I over beta, and we have looks like this, and we can regard this part as a probability of person I to brand J. Okay. Therefore, derivative of log-like contribution over beta is kind of so this is the error term, and this is xij. So we can regard x is this kind of orthogonal. We can argue that since this one should be 0, so which means that this error term should be orthogonal to the xij. Which we can think of as orthogonal condition. And similarly, if we take derivative of li over gamma j, and again this should be 0 to get a maximum value, then again this one simplifies into orthogonal condition over zi. And then we can also compare, we can also calculate the odds ratio. So this is probability of person I will choose brand J. This is probability of person I will choose brand J. So we can calculate the ratio of that, and the ratio. This part cancels out, so we have only this part. So it's a low exponential, so it is basically, it can be expressed as Vij minus Vij. So the odds ratio of person I will choose brand J or brand M is simply difference of the two values. One interesting property of multinomial logic is that it does not depend on characteristic of any choice other than J and M. Okay. So which means that again, to use the example of choosing a car. So suppose person I is U, and brand J is, for example, is like Hyundai, and brand M is like Toyota. So it is basically the odds ratio, the probability of choosing the Hyundai over Toyota only depends on the value of Hyundai and value of Toyota. So even if like the value of like Bench, Mercedes Bench, or value of like BMW goes up, the odds ratio of the two does not change. So this kind of property is called IIA, independence from irrelevant alternative. And this example, this kind of assumption, this assumption of IIA, so choice between Hyundai and Toyota does not depend on other characteristics, power and GM, Ford, and something like that. That sounds plausible in most of the cases, but not always. In some cases, the brand characteristic of other brand can influence the odds ratio between I and M. So brand characteristic, other brand characteristic, sorry. So this kind of independence of independence from irrelevant alternative does not always. Sometimes brand characteristic of some irrelevant alternative can actually affect the relative probability of choosing a brand over the other. When a Ford generates a new car, that can actually change the probability of choosing 현대 로봇이요. This is multinomial logic model, and for instead of extreme value here, we can also use normal distribution in this case, and we can also construct multinomial probing model. But this is extremely difficult, so people rarely use it. People don't use much about this multinomial probing model. Next one is ordered discrete choice model. I think this one is maybe less important. I can skip. Count data is actually important, but maybe too difficult for you at this stage. So let me skip. Okay. So I think I covered. I covered all the topic I intended at the beginning of this. So about the final exam, I think you can disregard this qualitative choice model. So I'll make a problem from here to here. Okay? So today's topic will not be included in the final exam, but instead you have to submit homework of the qualitative choice. Any questions? Okay, then this is the end. So please prepare your exam very well and see you next time.